Log on, tune in, find out. Another good idea from Cambridge.
So let me recap very quickly what we did this morning. So this is the physical situation. This photoacoustic tomography is a method that combines two methods. One is you take, for instance, a laser or RF pulse to the body, absorbs the light, you get a thermal expansion, then can I have the, what is this? No, the laser pointer, the laser point.
But there's a high-tech mechanical.
Okay, maybe that works better. Then this thermal expansion produces acoustic waves that are measured outside the body. And from that you would like to recover the optical properties of the domain, of the animal in this case. It's poor animal. Okay. So the first step, and I'm going to we just talk about this, is to solve a boundary value problem for the wave equation. So you know the initial data. I mean, you're trying to recover the initial data. You know the sound speed by making measurements at the boundary. And so this is the model for the problem. You have the acoustic wave equation with initial data f, and this is solved in the whole Euclidean space. There is no boundary condition here. Initial velocity is 0. F is supported in this domain, and you are going to make the measurements on the boundary of the domain for an interval of time. What? Okay, so the problem is to reconstruct f, the initial data, which comes really from a source, but I just made the reduction, initial data, by making these measurements. And this, as I mentioned before, this is a linear problem. Okay, so let me go. So we define one time. There are two important times here. One is the diameter of the domain with respect to this metric. I define this the morning. I come back to this again maybe tomorrow. And this determines the uniqueness time. And then there is the stability time. So you take the length of the longest geodesic, maximal geodesic going through the domain. So the idea is to have all the singularities. Again, I'm going to make this more precise, hopefully today. That goes through the domain. And the stability time is T1/2, meaning either the positive part of for positive time the geodesic gets out, or for negative time. And the theorem is for t bigger than this time, there is a stability, and for t less than that, there is no stability. Of course, if there is trapping, there is no stability in general. Okay, so I motivated a different time reversal. So the idea is to use the fact that the equation is invariant under the map sending t to minus t. So I consider at the final time, capital T, the boundary value h, but at capital T, I'm not going to put it 0 like in the time reversal method, the usual time reversal method, but function phi, which is harmonic, has boundary values, the values of this at capital T. And the map A that we define, which is going to be a pseudo-inverse, is the initial value of V. So you propagate this back. So you reverse the time. Okay, so I motivated that. And then you show that if you apply this operator A, which is also, I left it here, is F minus an error. And we have a precise control of the error in terms of solutions of the wave equation is the value at 0 of this equation that solves this is equal to 0 has a Dirichlet condition, vanishes on the boundary, and at time t equal to capital T is the value of that equation minus the correction term that we put, phi, which is the harmonic extension. Just use all the initial problem that we have. So that's the operator K that we want to estimate. And the theorem is that for T sufficiently large, bigger than the time of stability, then this is the identity minus an operator with norm strictly less than 1. And I'm going to prove that not for this time, a slightly larger time T bigger than T1. That is actually, yeah, I think that's what I'm going to do. And so this is invertible in the energy space, and you can find explicit. It's rare to find for a problem where you have a variable speed, variable coefficient to be determined, unless you have more conditions, such an explicit formula in terms of Neumann series of the f in terms of the data. H is lambda f here. Remember, the speed is assumed to, the speed everywhere here is assumed to be known. If T is even larger, so these are here, all the geodesics have left completely the domain for positive time and negative time, then this operator is furthermore compact. Okay, so I'm also going to show that. And then, so the summary of the dependence on capital T, how much time do you need to measure? This is the diameter. There is no uniqueness if you measure less than that. You need finite, because of finite speed of propagation. And if T is between T0 and the exit time for a what happened? The resolution looks terrible. What did I do? Yeah. Well, there is uniqueness, but no stability. Can you read this? Maybe I'm going blind myself. I don't know. If T is between T1 over 2 up to T1, T1 is the length of the maximum length of geodesics. So all the geodesics for positive and negative time have left the domain. There is a stability and explicit reconstruction. And if you are T in this situation where it's bigger than that, then the operator K is compact. So that's the best possible scenario. And I'm going to show now some examples of numerical experiments done with this. In the case, you can do, although the theorem says there is no stability for trapping speed, you can try trapping speed, because not all the rays are trapping, so only some of them. You still will get good reconstruction from the rays that are non-trapping. So with the numerical analysts here are Yan-Liang Qian and Hong-Kai Xiao. So this corresponds to the to a speed where there is non-trapping. This is the velocity, all the rays leave. So every ray has finite length. And this is the diameter. This is the domain, and the computations are done here. And this we chose this picture because it has a lot of textures. It used in image processing. They used to use a Playboy model to check all the, but then it became politically incorrect. So this is now what is used. So this is the Neumann series reconstruction. So we're taking T 4 times the diameter, and this is the error. Here is the time reversal. Remember, I mentioned you can always try time reversal. You just cut it up and define it to be 0 instead of this. And of course you don't get such good pictures, otherwise I wouldn't be showing them. This is a case of a trapping speed. You have a trapping speed here, and this is the time t0, the diameter. This is the exact initial condition. This is the initial condition, the F. That this is what we're trying to recover here. This is the Neumann series reconstruction after 10 steps. This is the Neumann series reconstruction with 10% noise, 15 steps. And this is the time reversal reconstruction. And with 10% noise, it's much worse. And here is Barbara with the same trapping speed now. The original, of course, since you have some trapping, the Neumann series is not as good. You can see some defects. And this is time reversal when there is trapping. It's much worse time reversal when there are singularities or things or rays that don't leave, because of you just define it to be 0 and you propagate back. So you create very strenuous rays when you propagate back. Okay, this is time reversal for the same trapping speed. Here is a radial trapping speed. Here the speeds are trapped. The geodesics are trapped, sorry. And this is another example that is used in image processing because it has a lot of texture, zebras. This is the Neumann series with 10 steps. And this is the time reversal with 10 steps and time. The larger that you have the time, the better resolution you expect. This is the radial trapping speed that I showed before for time reversal. And I think, and that's all the pictures I'm going to show. Of course, I want to show that the method is better. And I think it is better because it's based on an exact theorem, an exact reconstruction. Okay. So now I would like to give details of why the norm of k is strictly less than 1 and why is a compact operator is t is sufficiently large. So I'm going to use the blackboard from now on. Can I get the screen? There's somebody who's screen up here. Okay. So I will call this study of the wave equation in more detail. So we want to show the norm k in a nice space. I'm going to define it here is strictly less than 1 if t is sufficiently large. And we're going to have more precise notion of what sufficiently large is. So for the first thing that we have used about the wave equation is that, so you have this equation, we have already used this. You change time, it's still a solution of the wave equation. This is a very simple fact, but very important. That's the basis of time reversal. Second thing is energy, the notion of energy. So let's take the set omega, subset of Rn. If it is bounded, I assume that has a smooth boundary. Sometimes I'm going to just take the whole Rn. So the notion of energy of the solution, so assume for the moment that U is in C0 infinity of omega. So this means smooth functions with compact support in omega. So I defined this morning, but let me repeat it. This corresponds to the potential energy and then the kinetic energy. So for a time t. Okay, so the space of energy, the energy space. So let me denote this by h omega, is the completion of C0 infinity and then this no. Okay. Well, you will have to write it again. I'm sorry. Okay. And if you have a solution of the wave equation, then let's assume for the moment that U is in C0 infinity, then then you have that the energy is conserved. So let me check this very quickly, and let me so ddt. Let me just assume that U is real value, so I don't have to deal with U and U conjugate and so on. So this is the derivative, the gradient U let me call this ut times ut, the derivative with respect to time. So you differentiate this and you get, well, actually I should have said the energy is, I'm missing something here. People who know me know that I cannot get any constant right. It's 1/2, right? It's in 1/2 times the mass times the velocity squared, right? So this is 1/2. I remember here because I get a 2. Gradient of ut times gradient of u plus 1 over c squared of x, also a 2, so let me just cancel that, ut t dx, right? If I differentiate with respect to t. So now I use the divergence theorem, integrate by parts here, and I get the Laplacian divergence of the gradient, right? So I get, can you read in the back here? Ut times Laplacian of u with a minus sign, right? Because you're integrating by parts, plus 1 over c squared utt dx. So ut is a common factor here when I do this. but this is equal to 0 because it's a solution of the wave equation, right? So this is equal to 0. So energy is preserved. And for this calculation, I'm going to use this a little bit later. We only need u at the boundary is 0. You don't need the whole C0 infinity. When we integrate by parts here, we don't want to get contributions at the boundary. Okay, so this says that you have a group a unitary group define it this way. You have this, so this extends as a unitary map from the energy space the norms are preserved, right? Because the energy is preserved. What's the inverse, by the way? Ladies and gentlemen, what's the inverse? You had time reversal, right? What is the inverse? Please, somebody. Huh? You know that in China, I was told that if you go to summer school, you don't get reimbursed unless you pass a test at the end of the. So maybe maybe we should do the same here, right? It's U minus T, right? Okay, so that's the first consideration. So just during considerations of energy, I'm going to show that the norm of K is less or equal than 1. So the first step is we're going to show the norm of K. And now this is a bounded operator, will be bounded operator in the space which was H10 of omega. So this means bounded operators, linear and bounded operator. It's less or equal than 1. Okay, so let me do that. So the first little proposition, so here I have all what I need. U solves the wave equation in the whole space with initial data F. K is defined as the value at 0 of the solution of this equation. So the first little proposition is that U, T, and phi in the space H1, ut minus phi, sorry. Is equal to 0. So remember the space H1, the norm is the integral of the gradient square, right? Using H10. Okay, so remember this is 0 by definition. I hope I didn't erase it. Is the U or the V? Sorry. No, it's the U. Yeah. Okay, so let's take this. So what is this? This is the gradient of ut dot minus phi times the gradient of phi, right? In omega. Yeah. This is, by the way, the value of W at t equal to capital T. Okay, so now I integrate by parts. So if I integrate by parts, I get the Laplacian of phi. Right? How much is that? 0. Right? And I have boundary value 0, so I get 0. Okay, so from here, by just using Pythagoras, let me denote ut by definition ut dot. So by using Pythagoras, I get the norm of u squared. So I'm going to not to denote the space where I'm computing the norms is the obvious one, is equal norm of ut minus phi square plus the norm of phi square. Because this is orthogonal to this. So norm of ut minus phi square is less or equal is equal to norm of ut squared minus the norm of phi squared, and this is less or equal than the norm of ut squared. So this is positive. Okay, so why am I taking this ut minus phi squared? It's because that's the first part of the, that's one part of the energy of W. Remember, we're trying to estimate the energy of W, right? Maybe I will leave the energy there. Let me do this here. Okay, so let me I'm too jet lagged to remember all of this. I have to look at my notes. I usually don't use notes this time. So we get the following, that the energy of W, the energy is written there, of TW is the norm of ut minus phi square h plus the norm of ut t in L2. L2 is always denoted with respect to this measure, like in the energy here. Right? But this, by what we just proved a moment ago, is less or equal than, this is H1, the norm of ut square H1 plus norm ut square of x dx. What is this? What is this? H1 is the gradient of ut square plus the L2 norm with respect to the 1c square. So this means that E omega TW is less or equal than the energy, capital T of U itself, right? Because this is the energy of the solution. Okay? Questions? I'm trying to do this in some detail so you get a flavor of the type of things one uses. One uses a lot about the wave equation when trying to prove the result. Okay. So now E omega W0 We want to compute this because K of F is W at 0, and we want to estimate that, right? That's what we want to estimate the norm of K of F. Okay, this is equal to E omega WT. I'm doing here the convention that TW or WT is the same. The order doesn't matter. Why is this? So sorry? Conservation of energy, right? Because W satisfies a Dirichlet condition at the boundary. If I have it, did I erase it? On the right? Oh, here. That is 0 at the boundary. So the integration by parts tells you that the energy is conserved. And this is less or equal by what we just proved, UT. Right? We just proved that. And this is less or equal. U is a solution in the whole space. Right? But of course, you can define the energy in Rn. It's less or equal than the energy in the whole space Rn because you are integrating over the whole Rn, right? But now, what is this equal to? Again, by conservation of energy for the solution of the wave equation in the whole space, U0 times 0, right? Energy is preserved. So we have used conservation of energy twice here. But what is the energy at time 0? Look at the solution of what U solves. What is the energy of this solution? This gives 0. Does this work? This gives 0 to the energy here, and what do we get from the other side? The norm of F in H1, right? Okay, but what about this is W at 0. So this is part of the energy, right? Part of the energy of the solution at 0. The L2, the H1 norm, that's the first part here. So I get from here the norm of Kf squared is less or equal in H1, is less or equal to the norm of F squared in H1. And that's it. Right? So that implies that the norm of K is less or equal than 1. Question? You have a question? Okay, so now let's try to prove. How much time do I have? If you try to prove anything in detail, it takes forever. Let me try to, because I wanted to give a flavor of what is involved. Why is norm K less than 1? A lot of times, you get an error operator that you don't know much about it. It's a smoothing, for instance, you know, it's smoothing, but to prove that the norm is less than 1 is in general depends on something heavy. In this case, something heavy will be Tataru's unique continuation theorem. Okay, sorry. So now we check that as an operator from H1 to H1 is strictly less than 1. Okay. Okay, so for this I need some other facts, So we talk about energy for solutions of the wave equation. We have used time, the fact that you can reverse time, that energy is conserved, the notion of energy. The third thing that I'm going to use is domain of dependence. Or finite speed of propagation. That's one property which is very different from elliptic equations, that there is the speed of propagation is related, of course, to c. Right. So what is this? For instance, let me take the case let me take t equal to 0. We know that the support of f is contained in omega. Contained omega closure. I should have reminded you of this from the beginning. Of course, the data that you want is concentrated inside the region that where you are going to make the boundary measurements. So you can say, for the solution of that wave equation, what can we say? It's 0 to omega bigger than modulus of t. So it propagates. This is the standard wave equation when c is equal to 1. I drew it in that case. In the general case, when you have a sound speed, the distance is different. Remember, I defined the distance with respect to c before. So this will be coming from the light cones associated to the speed c. So it will be 0 here for distance bigger than modulus t. So you take, we're taking time positive only, but you take time negative, will be 0 there. Right? So that's domain of dependence for the wave equation. And something similar if it vanishes at some other slice of time. Suppose u vanishes at capital T and the velocity vanishes at capital T, you have a similar picture for times bigger than that. Right? You can just translate time. Okay, so the final ingredient in the proof that norm of k less than 1 is Tataru's unique continuation result, which I mentioned this morning. So t which in the form that I'm going to use it is the following. So because there are different forms to state it, so I'm going to state it in the way that I'm going to use it. Okay, suppose you have a solution of the wave equation in some domain. And u needs to have very little regularity. Even a distribution is enough. And suppose u is 0 on the ball with center epsilon, or center x0 and radius epsilon cross time. Then u is equal to 0 on the set xt, such that the distance is again in in the metric defined by 1 over c squared. In the case c equal to 1 is just the modulus. Here x0 plus modulus t is less than t. So let me draw a picture. So here is your, so you know the solution is 0 here. This is t, this is minus t. This is the point x0. This is time t equal to 0. So this is the ball of the cylinder, this cylinder here. Okay. Then this I'm going to draw it in the case of the c is equal to 1, but of course that's the this rays will be geodesics in the general case. So it will be 0 here. Again, you draw the light cone starting from every point. This is the outside one, and then you fill out this diamond type figure. So this is a sharp result, and it was a breakthrough when this was proven in 1994, I believe. For the case c equal to 1 or c analytic, this is Holmgren's theorem. And in the form that I wrote it here is also known as John's theorem, and also follows directly from Holmgren's theorem. So this is different than the domain of dependence, because this is time-like surface. The other one was space-like surface. So it's unique continuation from a time-like surface. So very powerful and deep theorem. And this is even valid if this depends on t, but has to depend analytically on t. But certainly from the case independent of t is true. Okay, so these are going to be the ingredients that I'm going to use to show that the norm of k is strictly less than 1. And I think I will do that next time, because it doesn't make sense to start now and then I won't be able to finish. It's not a complicated proof, but I need to go through the details. Okay, so exercise for tomorrow, how to figure out how to use A, B, C, D to prove that the norm of k is strictly less than 1. Hint, the proof proceeds by contradiction. So suppose it's not true, then all these inequalities, because then you will have an f for which norm of kf is equal to the norm of f, right? If the norm of k is 1. So all these inequalities are equalities. So in particular, the energy in the whole space Rn of u is the same as the energy in omega. So that means that u and its derivatives, ut has to vanish outside omega. And then you play with that. Okay, so exercise for tomorrow.